And in this summer, I've been working in Professor Tim Baidoo's lab in studying bacteria Streptococcus pneumonia. Today I'll be presenting on the title Functionalization of Graphene Field Effect Transistor Biosensor to Detect Streptococcus pneumonia. Bacteria has become a prevalent threat worldwide, and there should be the ability to minimize these cases. Almost 1.5 million people die of bacteria Streptococcus. This as a result of inaccurate and late diagnosis of these bacteria. For instance, clinicians prescribe antibiotics to treat bacteria, a perceived bacteria, but these bacteria survive these antibiotics, becoming resistant. Also, some other techniques and detection methods are used to detect these bacteria. Example, we have the bacterial culture. This method takes a longer time to detect bacteria. So, in our project, we are developing a biosensor device to selectively detect these bacteria and in the shortest time frame detect these bacteria. So, what is biosensors? These are sensors incorporated with biomolecules to detect not only biological molecules but other heavy metals and air pollutants. So how does these biosensors work? The biosensor has a target molecule which has a receptor which attaches to the target molecule. When this receptor attaches to the target molecule, it creates a physical change. This physical change is then passed through the transducer. The transducer interprets this physical change as electrical or optical. So in building our biosensor, we have two main procedures. We have the fabrication and functionalization. The fabrication will be explained more by Ms. Nadia. My work in this project is to functionalize this biosensor device. So what is the functionalization of this biosensor? This is controlling the graphene surface and modifying it, enhancing its properties to selectively detect the target molecule. In our case, we are detecting the DNA of Streptococcus pneumonia. In doing this functionalization, we first add a linker. Onto the graphene surface. This linker is a biological molecule made up of two functional groups, which attaches the probe onto the graphene surface. So after adding the linker onto the graphene surface, we attach a probe. This probe is a short complementary DNA of the target DNA Streptococcus pneumonia. So after attaching this probe onto the graphene surface, you use this biosensor to detect the DNA of Streptococcus pneumonia. So this brings us to my research question is the probe specific to detect the bacteria Streptococcus pneumonia? 2, is the linker able to connect the probe onto the graphene surface? I'd like to show you how we built the probe. As I said earlier, the probe is complementary DNA of the target DNA Streptococcus pneumonia. So we take a sequence of the complementary. We took different sizes of the complementary DNA of the target. We took 20 mer, 60 mer, and 120 mer. Then we added an amine group to this sequence, so that the probe will be able to attach to the graphene surface. for us to answer our research question about the specificity of the probe, we use a method called polymerase chain reaction. In this method, we have the double-strand DNA, of the Streptococcus. We heat it and we break it into single strands. After that, at the second step, the annealing step, we add a primer. This a molecule which starts the reaction. So after adding this primer, an enzyme called polymerase adds more nucleotides to this single strand, forming a new double-strand DNA. The second step, called the annealing step, is the step that makes it know whether the probe is specific or not. If the probe is specific, it attaches to a specific point on the sequence on the single-strand DNA. But if the probe is not specific, it attaches to different sequence on the single-strand DNA as you vary the temperature of the annealing step. So, after this polymerase chain reaction, it's impossible to use the naked eye to view whether the probe is specific or not. So we use another method called gel electrophoresis. This is where a charged molecule passes through a gel under electric current. So in this method, if the probe is specific, we will just see only one band on the gel. But if the probe is not specific, you will see more than 2 bands on the gel. So in our experiment, we used a control probe, a 20 ml, 60 ml, and 120 ml, and a negative primer. This negative primer is a molecule that cannot serve as a primer in the PCR reaction. So after the experiment, we can see that we have just single bands in each row. This suggests that our probe is specific to its target DNA. So we took just the 20 ml and annealed it at different temperatures to see whether at different temperatures the probe can attach to the specific target of the DNA Streptococcus pneumonia. And as you could see, we have only just single bands on the gel electrophoresis. This suggests that our probe is specific to its target DNA Streptococcus pneumonia. Also, for us to answer the second question about the linker able to connect the probe to the graphene surface, we use a method called probe recovery method. This probe recovery method helps us to know whether the probe is able to attach to the graphene, to the linker on the graphene surface. So we add the probe onto the graphene surface containing the linker, incubate it for 3 hours. Then we take the liquid on the graphene surface and measure the amount of probe in the recovery. So after measuring the amount of probe in the recovery, we washed the graphene surface and measured the amount of probe in the washed liquid to see the amount of probe in the washed liquid. So after our experiment, the initial amount of probe on the graphene surface containing the linker. So after measuring the recovery, we had just 30% of the probe in the recovery. Then, after washing the graphene surface, we just got 2% of the probe in the washed solution. So this suggests that we have almost 70% of probe added onto the graphene surface with a linker. And we did a similar experiment. We did a similar experiment with a larger size probe, the 120 ml probe, and we had a similar result. This suggests that our probe is able to attach to the graphene surface. Also, we did another experiment to verify, to see whether our linker and probe are able to attach to the graphene surface using a method called Raman spectroscopy. here, a light is incidented on a molecule. When a light is incidented on a molecule, the light wavelength is scattered into smaller wavelengths. These smaller wavelengths are processed into spectrums. The spectrums makes us know which kind of molecule we are detecting. So, in the literature we studied, it says that as you measure just the bare graphene, you will just get two peaks, the G and the 2D peak. But as you add more molecules onto this graphene surface, the G peak increases more compared to the 2D peak. Hence, the ratio between the 2D and the G peak decreases as you add more molecules onto the graphene surface. So in their literature, they added the linker, they measured just the bare graphene and added the linker, the one we are using in our experiment. They added the linker onto it and measured the spectroscopy. And the G peak increased more compared to the 2D peak. This shows that the ratio between the 2D and the G decreased as we add more molecules onto the graphene surface. So we use the same idea. We use the same idea in our experiment. We measured just the bare graphene. As you can see, the ratio between the 2D and the G is about 0.7. Then we added the linker onto the graphene surface. And we added the probe also onto the linker on the graphene surface. So as we add more molecules onto the graphene surface, you could see that the ratio between the 2D and the G decreases as we add more molecules onto the graphene surface. So we warmed the target DNA, Streptococcus pneumonia, to see whether the DNA can attach to the probe on the graphene surface. So after adding the DNA onto the graphene probe on the graphene surface, we could see that the G peak increased more compared to the 2D peak, hence suggesting that our probe and linker are able to attach to the graphene surface. In my conclusion, we could see that in functionalization of this biosensor to detect Streptococcus pneumonia, we have to know the specificity of the probe and also know whether the linker is able to connect the probe onto the graphene surface. And from all the experiments we did, we could suggest that the probe is specific to its target, Streptococcus pneumonia. And also, our linker is able to connect the probe onto the graphene surface. Thank you. I would like to thank Professor Tim Van Opijnen, Professor Ken and Annie, once my mentor, Mason, Marisa, and all lab members in Professor Tim's lab. Thank you very much.
So you used PCR, but that was only to test the specificity. The biosensor itself is not PCR based, is that correct?
No, we just use the PCR to detect whether the probe is specific or not.
So for the actual biosensor, is sensitivity an issue of like how many molecules are going to be there to detect, or is it so sensitive like that it's not an issue?
Oh, if you have, like, in our case, we'll be using a small amount of, either the concentration of the target DNA to detect, even if you have like 1 micro or picometer of the probe of the DNA, it could selectively, and it will be sensitive to detect this amount of concentration.
So the purpose of heating the DNA is to split it so it can attach to the probe, right?
Oh, okay. The DNA is double strand, so as you heat it, you break the double strand into single strand. And the probe also is complementary to that double strand DNA. So when it attaches to the single strand, then it can detect it.
I was kind of confused. So for PCR, okay, the amplicon, is it existing only Streptococcus pneumonia or other bacteria?
Sorry, I didn't hear.
Okay, you did a PCR for checking the specificity, right? Okay, that amplicon, that DNA part, is it existing only in the Streptococcus pneumonia or other bacteria?
Oh no, we used only Streptococcus pneumonia DNA. We used
Right,
only
so
DNA.
which gene is that? Which part? It is specific only if in other bacteria, if that gene part is there, you can detect all the other bacteria too.
No, that's where the probe comes into being. We just choose a specific point on the double-strand DNA of the target, Streptococcus. So if we choose that specific part, the probe will be only able to attach to a specific point on the DNA Streptococcus pneumonia.
But what gene?
Yeah, what gene?
In our case, we are using a target 4 or target 4. We are using target 4 or Streptococcus pneumonia. But the kind of gene we did, I have no idea about the kind of gene we use.
It's a perfect answer. It's a 16S RNA, so yeah, it's quite specific in this case. But the idea is recognize different genes, so or different material.
Okay, if there are no other questions, let's thank our speakers.